y, our dependent variable, or we also can call this explain variable or response variable, and then our x, we call this an independent variable or explanatory variable. So we could use x to explain our dependent variable. So we have intercept beta 0 as I said before, and then I have absolute parameters beta 1, beta 2 up to beta k, and then our error term. So this one just an example. So you have a model to estimate the use of baking oil based on two factors: temperature as well as the thickness of insulation used by different houses. Okay. So in term of interpretation, you can the use of variable the absolute parameters. After we estimate, we can interpret. So the estimation that the average value of y will change by the estimated value beta j hat for each unit increase in xj, each of the x, with all other variables remain the same, or we call this variables, meaning that the estimated value represents the amount of change, the average change in y per unit change in x, that particular x, while other x to be remain the same and not change. So this is an example of the way the number of interpretation. But later we estimate, we interpret on this one. This one the actual, the correct estimate, interpretation of the correct estimate. So beta 0 hat is estimate of the intercept. So they represent when all x equal to 0. So beta 0 represent the what we call estimated value of y when all x equal to 0. So for the bigger example, so we have the same data, the same file. So you use Excel, then you can just use that for the independent variable. So you can just do the same data analysis tools, data analysis. So the usage of oil is our dependent variable. So select regression. So this one your y, this one your y. So we can only set. So we just select this one. So your independent variables select both. So you select all. Okay, but numbers only do not select headings. Okay, so y and your x1, x2. Okay, so you get the estimate. So you have estimate of the intercept beta 0 hat, and then beta 1 hat, beta 2 hat. Okay, why we get different? Let's see. So in terms of interpretation analysis, so you can interpret as for 1 degree increase in temperature, the average amount of heating oil is estimated to decrease. Why decrease? Because negative decrease. So when x increase, y decrease. Okay, both negative. So it's estimated to decrease by 5.437 gallon, holding the other x to be remain the same, constant. And then for this one, for one each increase in the thickness of insulation, the average amount of heating oil is estimated to decrease by the estimated value 20.012 gallon, holding the other x to be x1 to be the same, okay, or remain unchanged. So now after you estimate, how to know how well our estimate, how good our model that we can use to make prediction, how good the model because eventually we want to use our model to make prediction. So this one, for example, to estimate, you get this our estimated value. So we can use this model to predict. They say when x1 equals to certain value, x2 equals to certain value, what is the predicted value of y? Make prediction. So how, now after we want to know how good our model in predicting the value of y. Okay, that can be done by looking at R squared. So coefficient of determination, the R squared. Total variation of y, which can be explained by variation of x variable represented by R squared or coefficient of determination. So R squared is calculated using SSR over SSE. SSR represents the total variation that explained by the total variation in the dependent variable. Okay, and SST is total variation. SSR is the part of variation that can be explained by our model. You refer to the additional note, this one. So this is our SST. SST represents the total variation. So y minus y bar, and then square, and we take sum of them. That represent the total variation in y. The variation in that dependent variable, the total variation that can be explained by the y itself. So you can either calculate SST using this, meaning you calculate average of y, and then you take the difference and then square for each observation. Then you take sum, you get SST. Or you can alternatively you can use formula. So you calculate the sum of y squared, sum of y, and then divide by sample size, you get the same. It's supposed to be the same value. So this is total variation in y, but our model can only explain part of that total variation given by this. So our model, after we predict y hat just now, after we estimate model, we have our y hat. So the total variation given by the difference between y, each of y, and the average y bar. Then, but our model can only explain this one, the difference between y hat and y bar. The prediction and the average. So this is the model our model can explain. So the part of the variation that can be explained by our model, this is the total variation. So if you take this, calculate this over, take ratio this, divide by this, so you get the percentage of the variation, the percentage of the total variation that can be explained by the model. Okay. So SSE is the remaining variation that cannot be explained by our model. Yeah. So again, if you want to know how good our model in making prediction or in explaining the variation of y, then you can just take ratio between SSR over SST. So that represents how many percentage of the total variation can be explained by our model. But take note that there is a tendency for R squared to increase when new variables are added to the model. For example, a model with x1, x2, and xe will have higher R squared with x1 and x2. So you have, let's say you have two models. One, you have two x, x1, x2. Another model, you have additional x, x3. So whenever we add new x, it will increase the value of R squared. Okay, so in that kind of situation, we not really able to identify or to know whether the inclusion of our new variable is useful to improve the model or not. So basically, the R squared is used to know how many percent of the variation can be explained by a model. But if your objective, you want to know whether additional x should be included or not. Okay, then you should not use R squared, because when you add new x, R squared will always increase. So R squared will not increase even though the new x variable added to the model is not relevant in explaining the dependent variable. So this is this disadvantage when comparing different models using R squared. So if you have two models, one model with 2x, x1, x2, and another model you have additional x, x3. So you want to know which one better. Do not compare R squared because the one that has 3x will have higher R squared. Okay, even though the additional xt is not really good, it's not really variable that explaining the dependent variable. So if you want to know whether inclusion of new variable is good or not,